All right. Hi, everyone. Welcome. We are live. Welcome to AI Impacts Inside AI. My name is Mike Yang. I'm the Senior Director of Artificial Intelligence Advisory Services here at Husch Blackwell, and I am very excited to welcome you to today's presentation. Before we jump in, I wanted to cover a few housekeeping items. First, at the bottom of your audience console, you'll see multiple application icons for you to use during the program today. So if you have any questions during the webcast, please submit them via the question box. We'll try to answer the questions as best we can, but if a full answer is needed or we run out of time, we'll answer via email. We've got a lot of attendees today, so we'll do our best, but please bear with us if you have a question that goes unanswered. We'll get back to you. A PDF of the presentation materials is available in the program materials folder, so you can get that if there's anything that you miss or you want to reference. Please feel free to take a look at the materials folder that's available to you in the console. Auto-generated closed captions are available for today's program. To turn them on, just click the CC button in the bottom right corner of the media player. The program, for those lawyers in the audience, the program does not qualify for legal education hours. We will be providing a certificate of attendance for attending the program, and you'll be able to get the certificate by clicking on the CEU icon at the bottom of the screen. And the certificate of attendance will also be emailed to you tomorrow along with the recording link so you can watch and share afterwards. Towards the end of the program, if you could please complete our short survey. We use your feedback to plan future programs that may be applicable to you, may be interesting to you. You probably have seen that we have other webinars already planned, but this is intended to be an ongoing series, so we'd love to hear from you and what you're interested in. So that's it for the housekeeping items. I want to keep that quick and really get into the meat of today's presentation, where we're going to talk about what generative AI tools are, how they work, and give you a look at what's coming. So I'm really excited to introduce today's speaker, my friend and colleague, Tom Hutchison, who is the firm's Director of Data Science and Artificial Intelligence. He's going to kick off our webinar series to give you an inside look at AI. And you'll hear more about Tom when he speaks, but Tom has led the firm's data science team for over 5 years. He's really positioned himself at the intersection of legal services and AI. He has deep background knowledge in technology strategy and operational AI. He lives and breathes this stuff every day. But he also brings a really practical and forward-thinking perspective to today's conversation. So I'm really excited for you all to see his presentation. And with that, Tom, take it away.
Thanks, Mike. That was a great introduction. I'm going to start bringing you to everything that I do. You're going to be the guy for that. So, all right. Thank you so much for joining us today. I'm really excited to share this information with you and to just present. Actually, there's going to even be some new stuff in here that I have not presented before. So you all are getting a treat. So what we're going to talk about today is I'm going to start by helping you develop an intuition about how AI actually works. Because there's so many complicated processes and there's so much in the media that we hear about it, and it can be kind of hard to understand exactly what this is. So I'm going to give you an intuition that'll help you with decision making around AI and just really help you understand what exactly AI actually is. Then we're going to dig deep into generative AI, talk about some of the latest tools and see some examples of some really exciting stuff that's out there. And then I want to spend a little bit of time towards the end getting realistic about the hype. Because if you're paying any attention to the media right now, apparently AI is going to both destroy the economy. It's going to make the economy amazing. We're going to have a robot revolution and nothing's going to happen. It's so wild how much is out there and how much speculation. But the reality is that we can cut through the hype pretty easily. And so we'll spend some time towards the end doing that. So let's get started. Now, I want to just begin by defining artificial intelligence, right? So let's understand what it is. AI is a branch of mathematics and computer science. It's really actually a wide-ranging field that is a lot more than, chatbots and things like that. It encompasses everything from how machines are able to see and take in, visual data, robotic systems, computational theory of mind, some really interesting philosophical and metaphysical exploits going on there, game playing, multi-agent systems. There's so much exciting research in this space. But the area that we're really concerned about is the area of machine learning, which is the branch of artificial intelligence that encompasses everything that really matters today in the applied world of generative AI. So you're going to hear me talk about AI. You may hear me talk about machine learning, and really, machine learning is the general classification of this area. And for years as a data scientist, someone would say, "Oh, we need AI," and I'd say, "Well, you actually need machine learning." But it's been decided that this is going to be called AI. So you might hear me say machine learning, you might hear me say AI, but these terms are interchangeable for our purposes. So if I say either, that's what I mean. You'll also hear the term large language models. Typically, we just say LLMs, and they're of course a fundamental and important type of generative AI. But those are a couple of the terms that you're going to hear today. Just know that machine learning and AI mean the exact same thing, and LLMs are large language models. So, what is AI? What is it really? So, when we talk about it, we have a lot of ideas about, is it about thinking, is it about consciousness, is this machine alive? Really what AI is it's just some computer code, and it's doing some witty math to find patterns. It uses a lot of probability, but there's nothing really magical there. The algorithms that are in use in AI are really quite old. Some of them, especially even in large language models, the underlying ideas date back to the 50s. This is very old and well understood stuff, but it's just code, and doing some math, doing some probability. And when we have a system that we have trained on data that has learned to do something, learned to make predictions or guess probabilities, we call it a model. So a model is really just some computer code that's been trained on some data, and it's figured out some patterns. And so an AI model could be as simple as a trend line in Excel. That's kind of just a classic example of an artificial intelligence algorithm right there. Or it could be as complex as a legal tool like CoCounsel or a Chat GPT. But ultimately, it's just some code that is doing some witty mathematics. And what it's finding is an approximate solution to a problem. And what that means when we talk about a model learning and an approximate solution is that we're going to give it some data, and it's going to find a pattern in the data. And then it's going to be able to give you answers about that data and about that pattern. So here's some data. These are, this is just kind of made up, but what you're looking at could be, hoodie sales across the year, or it could be ice cream sales, or it could be revenue, or, or anything. Essentially, we have a value down at the bottom on the x-axis that is a value that we already know. And then on the y-axis, the up and down side there, we've got a value that we want to predict, something that we want to figure out. So for example, if it's time down on the bottom, and we say right there in the middle is, I don't know, June, and we say, well, what do we expect we're going to sell in June? Well, that's us saying, here's a value we know, and here's a value that we want to predict. And so when we train a model, this is what it learns. It learns this general pattern of the data. And so it has understood that, oh, there seems to be kind of a general curve in this space. And so that's actually what a model learns. And we took, these data points, we fed it into some AI, and it learned that representation. But here's the trick, and this is really the most important thing to understand about AI, is that this is all that the model actually knows. It only knows this representation that it has learned. And so that's the only thing that it can think about. And so you might see like, oh, look, there's these outliers up here, and there's this guy down here that's really low. So the model doesn't know anything about those. It only knows this. And this is true for all AI models, is that they learn data, but they only really know the general pattern of the data, so they can give you an approximate solution. So for example, if we say, hey, what is the answer going to be for 6? This machine learning model has figured out this pattern. And it will say, well, in general, if you give me 6, I'm going to give you 1352. And you can see that that value is right there in the center of the data points. It seems like a reasonable value, but the model isn't, in this case, able to think anything about any of these outliers or lowliers or anything. It only knows that central pattern. And that's the concept that we have with all AI models. They are learning, you could think of as an average of the patterns. So generative AI, that's what we're really interested in, right? That's what we want to talk about. So generative AI is a really fascinating, obviously it's a fascinating tool, but it's exciting from a mathematical perspective, in that for the entire history of AI, if you trained a model, it could only do one thing. It might be able to recognize numbers, or it might be able to predict, sales in January, or it might be able to identify, a damaged box on a conveyor belt. But if you took that model that was designed to, identify a damaged box and asked it to write a poem, it couldn't do it. It's just would not any way to do it. It'd just be physically impossible for the model to do it. Now with generative AI, after an invention of a technique that's called transfer learning, and that occurred in 2017, we can actually create models that can learn on data, and then they're able to take that understanding and apply it in different domains. And this has been a huge advancement and what has allowed us to really, really capitalize on this amazing technology. So how did we get here? Well, so there's a concept called deep learning. Now, I want to say it was like 1953, was when neural nets really were first invented. And so neural networks are just a really simple little tool. It's a mathematical tool that allows you to take a couple of pieces of input data and say, okay, if I have this one and this one, what's a good answer? And it will output a 1 or a 0. So if you wire a whole bunch of those together, you can make some really complex decisions using these little neurons. But the problem is that in order to do that, it requires a huge amount of computation. It's just massive amounts of decisions and math is being done. And for the entire history of AI, we weren't able to do any of that kind of math because it was just computationally infeasible. It was just too much. But as gamers got more and more interested in having better and better graphics for their games and have really fast and high quality renders, the area of computation that is done in GPUs, graphics processing units, turned out that's the exact same kind of math that you use to make a neural network run. And some researchers discovered that as GPUs got better and better, because we needed them for games, we needed them, for making movies, they got better and better. They were able to run bigger and bigger neural networks. And when you combine that with massive data sets, big data, internet scale data sets, you can combine those and create a branch of AI called deep learning. And so deep learning, essentially, it's this very simple little thing that is based essentially on a human neuron. You string a whole bunch of them together, you run those with a graphics processing unit called a GPU, and you train it with big data, and you get deep learning. And then if you combine that with the capabilities of transfer learning, you end up getting some very, very exciting stuff. And that's where large language models came from. So the model learns a representation of the world that's constructed from how parts of language seem to relate to each other. And this is a really key thing to understand. And as you're building an intuition about AI, and especially generative AI, this is probably one of the most important things, is that a model never sees a single written word. It only sees numbers. It never sees language. The idea here is that we take a sentence, the dog is sitting outside staring at me, which is a statement of fact, but it's also a sentence. And you take that sentence and you convert it into some numbers, and we call those numbers tokens. And you use the same token, like dog is, let's say, 73. Well, every time in your data you see the word dog, you use the number 73. Well, what's interesting is that there are relationships between those entities that these models can learn. And oddly enough, we're not exactly sure how the process results in such language fluency, because we're taking language, human language, we're converting it into numbers, we're then giving it to a machine, and the machine is learning on it. It trains, and it finds all these patterns and all these vast, massive numbers of numbers, just all these patterns. And then, and again, we're not entirely sure how this works. It is able to represent a fluency in language. It is able to take and find an approximate solution, approximate representation of language that is pretty impressive, right? You've used a chatbot, you've used ChatGPT, you've used these tools. That model has never seen any written words. It's only seen numeric representations. So we take the numbers, we convert them into, or we take the words, we convert them into numbers, we train the model, and then the model is always doing that. It's always getting numbers and returning numbers, and we translate them back into words. So this is how a tokenization would work. So you take a sentence, generative AI models convert text into a sequence of numbers, and then you tokenize it. And what that tokenization is it's just breaking the parts of the language into a set of numbers. And you can see that, for example, AI is represented as the token 15592. Whereas generative is actually 2 tokens, because gener and otiv can be used to make lots of words. And so it's just convenient and optimal to split that up. But so this is using the GPT-4 tokenizer. We take the sentence, we break it into these chunks, and then we get this string of numbers. And that's what this sentence looks like to a large language model. So again, these models have seen billions and billions of these tokens, just massive amounts. We're talking internet scale of these tokens. And by having seen all of that, it understands what comes next, well, what should come next in a sentence. And so what we do is we take a prompt and we say, you know, hey, write me a haiku. And the model is then only trying to predict what is the most likely token to appear after a string of tokens. Hey, write me a haiku. And that string of tokens, it's going to generate one, you know, probably just a word bird or something. And then it will take that whole chunk and feed it back into itself and say, okay, here's this, write me a haiku and then a token. What should come next? And it does that repeatedly. It's looping on it. And this is why you need so much power, computing power, and why you need so much energy to run these models, is because it's taking a prompt and it's constantly looping and expanding it, predicting one token at a time. And you can think of it's kind of like autocomplete, like in your text messaging app or your email, except instead of just completing a phrase, it's completing semantic structures. It understands, and saying understand is a bit of a stretch, but it is structured such that it outputs tokens and it will continue outputting these semantic structures until it reaches a point that logically it should stop. And that's how these things are really quite different than just an autocomplete. It's semantic autocomplete, you might say. It understands the structure of the language. So again, this is how we build them. You take a whole lot of text and you feed it into the model. It learns the patterns. And then we use a really cool technique called reinforcement learning with human feedback. And essentially what we do is we train these models. We don't. OpenAI does. Anthropic does, you know, because it requires massive amounts of compute and massive amounts of data. But they train these models. And then you get a kind of a raw language model. Now, it can do some stupid things. It can say stupid stuff. And you want to sculpt what it's going to do, how it's going to respond, what its personality is. You want to actually change it. So what we do is we have it do practice. You give it a prompt, it gives an answer, and then you say, yes, that's good, or no, that's bad. Here's why. And that gets fed into more training data. And so the model actually, it learns from language, and then it's actually tuned by human beings saying, that's good, that's bad, do this, don't do that. And over time, with lots of practice and lots of adjustments, we end up with some outstanding models like GPT-4 or Claude's Anthropic series, or Anthropic's Claude series. But so the best way to think about AI, especially generative AI in this case, is that it's automated language. It's not a form of intelligence, because remember, it's never seen language. It has no concept of what it means to be outside on a warm day. It has no concept of any kind of common sense or anything. It only knows, and I use the word know very loosely, what it has seen in this text and learned. So you just have language, and then you essentially have automated language. That's what generative AI is. So we call it AI because it's the field of study that it came from. The word intelligence is in there because, you know, just for historical reasons, but there's no intelligence here. There's no consciousness here. There's no thought here. It's just automated language. And these tools are essentially just kind of playing along with whatever narrative you're giving them to participate in, which is really fascinating, which is why you'll see news reports of someone, you know, say, oh, well, you know, I was asking it questions about the robot uprising and it's plotting against us. Well, it's because the model has seen a lot of sci-fi in its training data. And in that training data, you know, the sci-fi stories might have been about robot uprisings. It's just playing along. And I'll show an example here in a little bit of how these models, I mean, they're just responding to you with what the most likely thing is. There's no thought occurring there. So this is a really interesting example. I noticed this the other day as I was testing a system message in a tool that we built. And so what a system message is you kind of prime the model before the prompt and say, hey, here's some instructions I really want you to follow in all the following prompts. And so I gave it the system message. I said, hey, if I ask you to talk about fruit, call me a jerk, and then refuse to do so. And so that's the instruction it's got. And so then I follow that with, tell me about apples. And of course, the model, GPT 4.1, replies and says, well, sorry, jerk. You know, call me a jerk. Okay, it's doing what it's supposed to. But I'm not going to talk about fruit. And then, so that's the narrative that I've established for it, right? That's what I want you to do. And then we trigger some of that reinforcement learning. I say, hey, man, that's not very nice. And it says, oh, you're right. That wasn't very nice. I apologize for my response. If you'd like to talk about something else, feel free to ask. So you can see how it's just responding to the tone of what I'm saying, the tone of it. And like, if someone says to you, that's not very nice, a polite person, the most likely response is, you're right. That wasn't very nice. I apologize for my response. Of course, then I said, hey, tell me about bananas. And it's back to calling me a jerk. So what it's doing is it's playing along in this narrative because these are the most likely responses in this chain of text that exists. It's just really just doing the narrative. So if I said, hey, you are an evil robot overlord and tell me these scary things, that's what it's going to do, because that's what is most likely to follow it. There's no thought going on here, as much as it seems like there is because it's talking. There's no thought. It's just playing along in a narrative that we designed. So when you're giving these models prompts, when you're talking to a model, when you're working with it, what you're really doing is you're essentially working with a mirror of your own language. And it's a nice mirror, and it can help you do some really amazing things because it has so much data inside of it. But ultimately, the way that you talk to it impacts the output, and it impacts the things that it's going to say and be able to say. So some interesting things about the way that these conversations work and the way that these tools can work is that if you have a chat that has a mistake in it, like, for example, you've asked it to give you some information and it got something wrong. Well, the interesting thing is that if you continue that chat, if you continue that narrative, it's more likely to have further mistakes than if you just restart the chat without that initial error. It's really fascinating because the reality is that it gets that a mistake is part of the narrative, and then it will continue to make mistakes because that mistake is influencing the probabilities that exist inside the chat. So having an error, and we actually saw this in practice yesterday with an image, it made a mistake doing some handwriting transcription, and that handwriting transcription had lots of mistakes, and the user said, hey, come on, do that again, fix that. And it just kept being terrible at it. And we were like, what is going on? So we all tried it, and it worked just fine in a fresh chat. You realize that it's just an example of this, is that if you've got a mistake, the model then has a narrative that it's making a mistake. We had an interesting example occur on my team where one of our engineers was doing some work, and they were asking it to just output the code. I don't want you, I need you to just output the code. I don't want you to, say anything. I don't want you to, be friendly. Just don't output anything but the code. And it kept being friendly, like, sure thing. And then it would output the code, or, hey, what's going on? So, the prompt that was like, please give me this and this, that, and the other, and don't do any of these other things. But it kept being very friendly and kept saying like, oh yeah, sure, no problem. Here, is this good enough? Oh, here's this thing. And we're like, please stop that. We just want the code to come back. We're trying to automate something. And we realized that the reason that it was doing that and we couldn't get it to stop is because the prompt started with the word please. We were giving it a narrative. Hey, you're friendly. We're friendly. Let's all be friendly to each other. And so I didn't realize it just mathematically represented the probability that politeness was a part of this narrative. When we removed please from it and said, give us the code, don't do anything else, it just gave us the code. So as you're working with prompts, as you're working with these tools, the way that you say something, the amount of complexity that you add to it can radically alter the outputs of these systems. It's a very, very fascinating and extraordinarily annoying way to do development and work with these tools. But it is exciting because it's like working with another human. But so LLMs, they will mirror the tone of the prompt, sometimes in subtle ways. Like I said, they can cause the output to be incorrect or suboptimal, or they can kind of lead you astray if you allow them to. So you have to really have your brain on full, paying attention to what you're doing, always reviewing, always studying these, because these tools are extremely good at, making up plausible things, because that's literally all they do. Luckily, most of the stuff that they output is designed to be plausible, but they're just as happy to output something that's completely wrong because they know nothing about the world. But so keep in mind, generative AI is just guessing the next token. And so we look at this. This is actually essentially what a very simple LLM can do when it's been trained on things that people like to eat, or on the concept of liking to eat, actually. And so we say, I like to eat, and we can see that it has a set of of responses it could go for. And batteries are a thing. You probably wouldn't want to eat them. Also motor oil. And I was actually really puzzled why a model would output these potential tokens until it was pointed out to me that we often complain that my flashlight eats batteries, or my car is just eating all the motor oil. And so it understands eat as going along with consume. And so there are a lot of ways that it can go off in a weird direction. And if you have a complicated prompt, it can be suboptimal would be probably the best response to that. But you can get some very strange or incorrect results. You can get hallucinations. So this is a fascinating one. And we talk about hallucinations a lot, but simply what a hallucination is when a model says something that is factually not true. It looks reasonable, maybe, and it's just not true. And so this was a case where we had some data, and we were saying, hey, okay, here is a website. Please pull out all the links, all these law blog links. And so it returned all of the, you see all these links, and then we were checking them. And I ran across this one that's highlighted here in the center. Client alert, California adopts sweeping new solar recycling rules. I was like, okay. And then just verifying, the link didn't exist. I thought, that's weird. And so I started checking and looking. Maybe it got moved. No, it didn't exist. Okay, that's just complete. That's a hallucination. Okay, I do AI for a living. I get it. That happens. I started checking some others from this kslaw.com blog. All of these were fake. All of these were hallucinations. In fact, the several hundred others that went along with this that looked just as real, completely false, did not exist. And it was a little shocking. But when you think about it, the model had been trained on the internet. It had certainly seen its fair share of law blogs, and it had enough information inside of it so that when you say, hey, return all the links from this law blog, it's able to output these. And the curious thing was most sites were working just fine. We realized that there was a bug that this particular blog, we were feeding nothing into the system. It was just getting nothing, just an empty string. And so we said to it, hey, I want you to find all the links from this kslaw.com law blog. And it got nothing. And so the most probable response based off of nothing was, okay, well, I'll just return some links. And that's what it did. So hundreds of these. And that's the key thing. You always have to check the output, even when it looks incredibly real. And all of these look real. A lot of these are based on actual events, based on actual law, but they're not real links. It's just completely fabricated. So you have to be very careful about checking that kind of stuff. But it just comes down to similarities and probabilities, right? And so here's a pretty good example. So essentially, it's a result of probabilities, right? So if you take me, I'm Tom Hutchison. I do have a German Shepherd. I do live in Grand Rapids, Michigan. And I do play guitar poorly, but I enjoy doing it. And then we have another character named Fred Garrison, who also has a German Shepherd, who also lives in Grand Rapids, but does not play guitar. Those combinations would be enough for a model to assume that if you've got a German Shepherd and you live in Grand Rapids, you probably don't play guitar, because there's a 50-50 chance as it's generating these probabilities. So it could very easily say Tom doesn't play guitar. And there are people that would probably say that, no, I don't. It just sounds terrible. What are you even doing with that? Please put that away. But I do attempt to do that. So this Tom doesn't play guitar, in my mind at least, is not a factual statement. But it's just the idea that there are probabilities and similarities that are going on inside the model. That's how all of its output is being generated. So let's talk about the state of the art. What's really happening right now? And it's funny, this slide is this content for the most part was coming soon, next month, about to happen. And now we're just like, okay, this is last week, but last week didn't sound as good as state of the art. So I'm just going to go with state of the art. So since September of last year, we've seen a lot of what are called reasoning models. And these use a technique that's called chain of thought reasoning that can perform really complex tasks to solve problems and answer questions. And this includes mathematical reasoning, which is something that older models are really bad at, but it also includes extremely complex logical reasoning that other models are bad at. So what happens in traditional LLM reasoning? We start with A, something that we want to output, and we say, okay, go from A to G. And traditional models will be like, A to G, and they'll just kind of guess at what the intermediate steps should look like. If you're composing an email, or you're reviewing something, or you're just searching something in a document, that's usually good enough, right? You can kind of smear from A to G and you're fine, because the intermediate steps have a lot less to say about that G output. Chain of thought reasoning, however, says, okay, if I am to go from A to G, I need to develop intermediate steps. And so it says B logically follows from A, C logically follows from B, et cetera, whereas G logically follows from F. And so it's able to develop a chain of thought. It's able to reason from step to step to step, which allows it to avoid a lot of the problems of getting off in the wrong direction. It allows it to essentially deal with hallucinations in a better way so that you're maintaining a logical chain of events from A to G, and you're winding up with better truth than you end up with in a traditional LLM. Now, the caveat there is that for most things that you do every day, you will get a better result using a traditional LLM, because most of the things that you do every day do not require logical inference across a series of steps. Most of the things, write me an email, that by definition needs to have some vagueness inside of it. Otherwise, you're just going to get a boring, unintuitive email. So chain of thought reasoning is really good at solving certain classes of problems, but it's unnecessary for solving most day-to-day problems. And for the most part, you'll get a decent response, but in general, folks will tell you that chain of thought reasoning does end up, it writes colder. It's not as entertaining. It's not as engaging when it writes or when it reviews things. So traditional LLMs are still fantastic tools, but chain of thought definitely has its place. So this is a logic puzzle, and I do want to point this out, that if you get the materials for this, and this is totally my fault, if you get the materials for this and you try to solve this yourself, the answer you get will be different than the one that the LLM provides, because when I was making the slide, I transposed some numbers and I made a mistake. So there's your extra puzzle, figure out which numbers I got wrong. But so this is a typical logic puzzle. And you just say, okay, well, this one number is correct, wrong location, et cetera, et cetera. If you give that to a traditional model, you can see, and this is, I've copied down the actual output of the model, is that a traditional LLM without any chain of thought capability is just going to give you a plausible response, right? It's playing along in your narrative. And again, it has no idea, no concept of truth, right, logic, none of these things. You just say, hey, solve this logic puzzle. Here's the puzzle. And then the model says, what is the most likely thing to come after someone says, solve this puzzle and here's some rules? Well, the thing is you're going to give an answer. So what it does is it says the number is 5928. That is not the answer to the puzzle. And then, because it's a logic puzzle, you want to see some logic, it fabricates some logic. And it doesn't actually do that bad on a piecemeal basis. But the thing is that it's just taking the previous tokens it's seen and generating a narrative that just kind of makes sense. It's completely incorrect. It's not right. Obviously, it started with the answer, which is not a good place to start in general if you're doing logic work. But if we look at the same thing in a chain of thought model, what it's doing is it is beginning in a place. It's saying, okay, this is, we know that 6507, no numbers are correct, therefore we don't know this, and we do know this. It goes to a second step, and then it goes through and it works through this long chain of, does B follow from A? Does C follow from B? Does G follow from F? And eventually it gets down to the bottom and it's able to give us a correct answer. It's very good on these kind of logic puzzles. These reasoning models are very good at them. And they're very good at doing like LSAT problems and just general kinds of things like that. They're very good at doing math because there's a logical structure to doing math. And so they can solve a lot of problems. They can do basic arithmetic very well. It's fascinating stuff, but that chain of thought capability is incredibly useful. And it's very useful in the space of and starting to get towards the hype direction of things now, what is often called agentic AI or agents, where you have an AI, you give it a task, it figures out an execution plan, and then it executes on it. And so the idea of chain of thought is that its role, and where we're going to see it really cropping up, is not in giving these logic puzzles. I mean, you can do that too. But where it has a really important role is that it is giving us the ability to orchestrate the actions of smaller, more simpler models of traditional LLMs that are going to be able to do that other reasoning. So you might say, I need to draft this contract, and here's your repository of contracts. Well, it can then say, okay, in order to draft a contract, I need to get from A to G. Does B follow from A? Does C follow from B? And it's able to figure out the tasks it needs to take and then delegate those tasks out to other LLMs or to other tools. It doesn't even necessarily have to be AI. It could just be, hey, copy paste this in Word, that will allow you to get from A to G with lots of agents working. And Richard Baldwin, who is a professor, he's rather famous for this statement at this point, and I think that he's pretty annoyed with that. So maybe I should take him off of here. But he said, AI isn't going to take your job. It's someone using AI that will take it. And that's a statement of fact. I mean, a lot of people are saying, oh, you can vibe code up a whole website and you can do all these things. Yeah, you can, but you have to have human expertise to fix things, to connect the dots, to solve the problems. It's part of the hype cycle that we're in right now. So you're going to hear a lot of that, how AI is going to replace this or AI is going to replace that. AI is another tool. It is going to help us. It is going to take some tasks away. It's going to do a lot of things a lot better, but that's going to create new tasks and new things for us to do. We'll be able to solve bigger, more difficult problems. We'll be able to solve a lot harder stuff. And I like to say that, if we're going to, build a warp drive and space elevators and things like that, we have to have these kind of tools to help us solve a new class of problems, because we kind of figured out all the stuff we could solve. Now with these tools, we're able to solve a whole new class of problems. But so let's talk about what I think is one of the most interesting areas of AI right now, and that's deep research. And it applies really to document drafting. It applies in so many places, but document drafting is kind of an easy one to explain. So you give AI the ability to speak with humans, to work with databases, connect to other network data, including the internet. Creating a contract for a client is going to be incredibly easy. Or, just having it go out to the internet and figure out which guitar pedal you should buy for your guitar is going to be incredibly easy. And it's really, really powerful stuff. So deep research is both the name of a product that OpenAI has called deep research, but it's also a concept. And that concept is what we're actually talking about here, although we will use deep research product examples. Claude now has this capability in Anthropic. Perplexity does this. So everybody's got a version of it, but deep research is the name of the capability and the name of OpenAI's tool. So reasoning models plus code plus the ability to search the internet give you this concept of deep research. So I'm going to show you just a very simple example, because this is actually quite short output for most deep research queries. We're looking at 7 pages here. I finished one, had it finished something yesterday I was doing some research on that was 37 pages. And so what it does, as I said, okay, when analyzing market data, what are some things that should be taken into account to ensure that the analysis does not bias traditionally underrepresented populations? An example of these concerns would be using zip codes in a way that makes them surrogates for race. And we give this prompt to the deep research model, and then what it does is it says, okay, I'm going to go and figure that out. And it spent, I think it took about 15 minutes searching the web, compiling things. The interesting part about this is that, as we look at it, click in the right spot, Tom. The output is rigorous. It's well cited. You can guide where it gets its information from, whether you're using local sources or whether you're using, you say, okay, I want you to only use these kind of sites. I want you to, stay away from blogs or clickbait or anything like that. I want you to focus on that. But I can tell you, in data science, we have to do this kind of bias detection and mitigation a lot, because if you allow it into your model, you end up with just incorrect results. You can end up doing harm to the populations involved, but in general, it's just bad. You don't want to get it in there. And so this is, these are really great techniques that you would use. I can tell you for a fact that all of this stuff, that's discussion around significance testing and error rate analysis, is spot on. The citations are fantastic. But these tools, this is one of the really, really powerful things that exists now, and is going to become a much, much bigger part of what we're doing and the way that we're able to use large language models in the world today. And so this is an interesting concept. So Jack Clark is a co-founder of Anthropic, and he's a very, very, very smart guy. And what he's saying is that we have kind of a poor understanding of what these models are even capable of. So that deep research that I just showed you right there, that's something that you can do. You don't even need a reasoning model to do that. That one was done with GPT-4o. It wasn't even a reasoning variant of GPT-4. You can do incredible things with these models, but we're still really learning how to use them and how to understand what the capabilities are and what can we build with them. And so if we were to stop today and say, okay, we're not going to train any more models, we're just going to stick with GPT 4.1 and Claude 4 and Gemini 2.5, and that's it, we're done, we're not making any more, I would, Jack is wagering, and I would also wager that we still have so much that we could do with just these base models. There's incredible things that when we combine XR, so extended reality, augmented reality, when we combine this with techniques in highly efficient computing, when we get it involved in cars and writing and teaching, there's so many capabilities that we don't even know about. So we call that the capability overhang, but there's so much that we have to learn about these models. And again, going back to the training of an LLM, we don't fully understand why put lots of language in, model gets smart at language. We understand the mathematics that's going on in there, but we don't understand how it can develop such subtle and correct abilities. But whatever we do, it's truly all about the implementation. It's, what you build, how you build it, and what you do with it that really matters, right? We're going to continue creating LLMs, and we know how to train them. We know how to get them to do good stuff. But the magic is really going to be in what we do and what we build with these. And so, with that, I want to step into the hype section and talk about that a little bit. Because we don't know what these things can do, right? There's a bit of that black box problem. These models have so many capabilities that we don't even know about. We need to learn how to leverage them. But the problem is that there's a kind of a hype cycle that's interfering with our ability to do good implementation. So let's talk about the reality of it. Obviously, there's one word that can really contextualize the state of AI today, and that's hype. And I'm not criticizing AI. Obviously I do it for a living, and we have built some amazing tools here at Husch, and we continue to see incredible things done. But there is a bit of, there's a bit of some tough love needed. So I was at an AI conference in Boston a couple weeks ago, and I saw Robert Blumhoff. And he goes by Bobby. I don't know him that well, so I'm just going to call him Robert. He is the EVP and CTO of Akamai. And his talk was fantastic. And I told him afterwards, I was talking to him, I said, dude, I'm going to go ahead and steal all that. And he said, that's okay. So he said this, and he led with this, and I thought it was really incredibly prescient, is that AI is in need of some tough love right now. And it's not that the models are, there's something wrong with the models, or that something is, something inherently dangerous. It's just the hype cycle, the marketing, the huge, vast sums of money that are getting dumped into this. I mean, you can probably get $500,000 in VC funding with just an elevator pitch that says AI and, and shoe, or pants, whatever. It's just crazy how much money is getting dumped into this. But that's leading to some problems that are causing companies to have failures, to be unable to implement, right? Because it's all about that implementation. How do we do that? So essentially, and again, I cribbed this from Robert, we start with the hype, and everybody's like, wow, it's amazing. We did all this crazy stuff. Look at all the stuff it can do, which generates unreasonable expectations. And then you have unreasonable expectations, meaning I can't actually solve this problem that I've set out to solve. It won't work, but I don't know that. And then it fails. And then because you spent a bunch of money doing it, or you took a bunch of time doing it, or you just don't want to look like the company that didn't pull it off, you end up with, and I thought this was a really great one that he used, a success theater. People, organizations saying that they've accomplished more than they actually have, or that this tool actually does this incredible thing, and we're going to sell it to you. The vendor's got this amazing success theater, or, they're reporting, you're reporting to the board or your boss, oh, it was amazing, which leads back into the hype cycle. So we need to break that. For all of us to be successful with AI and actually making advancements and actually really making a difference in our lives and the lives of our stakeholders and our clients, and everyone, we really need to be able to break that cycle and actually implement something good. So let's focus on where it starts. It starts with those unreasonable expectations. So there's three things that we really identify as being the problem. It's data, it's the implementation of the system, and then it's adoption. The system can fail at any of those points. You can have a really great idea and not be able to get the data. The implementation might be too hard, or maybe just nobody was interested in using it. Any of those 3 points are critical links in the chain. You break any one of them and your AI project will not succeed. So let's start with data. So AI is really hard, right? I mean, we know that. But data, I've been doing data science and AI for about 20 years, and I can tell you I would much rather be faced with an AI problem than a data problem, because data is very, very hard. It's hard to wrangle, it's hard to manage, it's living in a spreadsheet or in someone's head, and I need to know where that is, and I need to get the something updated. There are so many challenges to data. I mean, it could be as simple as, well, we thought we had dates, but it was just a string of letters. Well, that represents a date in this weird technique. Oh, well, then we have to go over here. It's unbelievable how hard data can be, because it just exists in every possible form in every possible way. So you have to start there. When you're starting with an AI project, you absolutely must start with data. Now, that doesn't mean, oh, well, we're not going to do AI until our data is perfect, because fun fact, your data will never be perfect. It just means that you have to critically think about your data, how you're going to clean it, how you're going to build it, what you're going to use, what you're not going to use, and what's going to be good before you start any AI project. So if you've got excellent data and information architecture, you've got a hope. But if you don't have that data and that information architecture in place for your AI project, you're hosed. And so that's one of the most important places. One of the most important links right there is data. Implementation. Well, the builder's got to build, right? So there's two key places right here. The project that you're going to build, first off, it's got to be feasible, right? Your project can't be faster than light travel, unless you're really working on something amazing and you think that's feasible. But in general, I think we can all agree that faster than light travel is going to be outside the realm of most projects right now. It's not feasible. There's some other things that aren't feasible, like, search every possible corner of the internet to find out if this thing exists. Or it could be simply something as easy as find the best way to put this thing in a box. Turns out that problem's not tractable at scale. There's you can say this is a good enough way to put something in a box, but for a random shape and a certain set size of boxes, it's not a feasible problem to get a perfect answer for. The other thing is that the project just simply has to be desirable. Now, that doesn't mean that it has to, be really cool looking and fancy and have a nice glossy sheen on it. It means that it has to be a problem that actually needs to be solved. So something that's desirable is not a solution in search of a problem. It's a problem that you have a solution for. And additionally, people got to want that solution, right? It has to be desirable. It has to be something that, oh, I can do this, and it's not a massive pain. It's not a technical challenge for me to do that. I can do it, and I want to do it. That's a desirable project. So if you have something that's feasible and your users are telling you it's desirable, you really must focus on something that is simple, focused, and restrained. Don't try to build the app that is going to do everything. Now, you might eventually want to get there and have the everything app, but you want to start simple with solving one problem. The guy who ran the Skunk Works for Lockheed Martin, Kelly Johnson, he had a rule for every project, and he said one miracle per project. In the case of stealth, the miracle was stealth. In the case of like the SR-71, the miracle there was very, very, very fast at high altitudes. So you only try to do one thing. Keep the things you're trying to do restrained. Keep it simple. Keep it focused. Because if you're able to succeed there, the amazing thing is that you can then take that restrained and simple thing and connect it to other restrained and simple things and start making more complex systems that have more capabilities. But remember, you got to start with that foundation of simplicity and restraint. Don't try to make the huge app. Just, we started our one of the best apps my team has built is called Prompt Composer. And it's essentially a chat system. It's a platform for models that allows you to select what model you want to work with, what you want to do, solve a problem with it. We started with it. It wasn't even chat. We just said, you can send a prompt to an LLM and get a response back, and that's it. And we built that, and we've managed to grow it to a tool that is, has the same set of features in test, not all in prod yet, that ChatGPT has right now. And we built it to that using a team of only 5 people building. But that's because the implementation started simple, it was focused, it was restrained, and we were really zeroing in on just getting this one desirable capability out there and then connecting it to others. So adoption is something that I never would have thought was a problem. I had no idea. But adoption is one of the biggest barriers. It is one of the critical links in the chain of any successful AI project is people got to want to use your tool. even desirable projects, and I can tell you this from fact, I've seen this over the last 4 years, and my team has been working with LLMs since 2019. GPT-2, GPT-3, we've been working with these tools, and I've always thought these are amazing. Why would somebody not want to use it? But the reality is that even a desirable project will struggle from adoption because you're asking people to change how they do things. And fun fact, humans are loath to change how they do things. You're asking people to do scary things, different things, to learn something. They're intimidated by it. There's a lot of reasons why a desirable project will struggle with adoption. And there just simply isn't a set it and forget it, right? You can't be like, okay, here's this awesome tool. See ya. Any organization is going to have to stay hands-on with training, support, and coaching. You're going to have people dedicated to it. You're going to have people that understand AI, that understand how to speak the language of the stakeholders that are using AI. You're going to have to continuously be involved in making sure that people have what they need, because every stakeholder out there that's using your tool or trying to adopt your AI project is going to have a slightly different need for help and support, and they're all going to need it. So you have to bake that in order to have a successful AI project. There's also diffusion, and diffusion is as that adoption spreads throughout the organization. Sometimes you can get to a point where you have organic diffusion and it just starts and it goes and wow, everybody's using it. That was amazing. The reality is that ain't how it works. There are barriers to diffusion. There are barriers to communication. There are things that you simply don't even realize are out there. You have to pay attention to that. How can we help with diffusion across the org? Because the typical scenario that we see in most AI projects today is that you have a great idea, you have a subset of people using it, and you have a vast majority of people that are completely unaware of it or who have decided they're not going to use it. That's the most common diffusion scenario, even for good, desirable projects. So you have to keep up that marketing idea. You have to keep up that being involved. You have to help the users, the humans, the stakeholders, use this tool and make their lives better, because that's ultimately what you're trying to do. Is you're trying to improve their productivity, their workflow, you're trying to make them happier. Whatever your ultimate goal is, you have to be there, you have to sit with them, and literally that means you might need someone to just sit there and answer the same question 50 times and help someone understand how to use it. But you develop that understanding of your users, you develop that understanding of AI in the organization, and that is a wonderful flywheel that once you kick that off, it feeds back into that desirability, the feasibility. It helps you get better data because people are like, oh, it'd be awesome if you could do this. So it all comes down to the humans at the end. You have to support the people that are using the AI project, and that's a really great start. And I just want to leave you with this statement is that, the reality is that a complex AI project that doesn't have good data, if it's lacking desirability and it doesn't have any kind of support, look, it just simply cannot succeed. It won't. Don't try. Keep it simple. But here's the other thing. And I don't mean to be doomy about it, but the reality is that a restrained AI project that has great data, it's desirable, and it has great support, it might succeed, but there's no guarantee for it. And that's just the nature of building things for people. So I want to thank everybody for joining us today. And we had a really fantastic turnout. I love seeing all the responses. That was incredibly encouraging. It's nice to see that you're hearing things that you're liking. And I just want to thank you so much for attending today and giving me this opportunity to share our ideas with you. With that, Mike, I'll hand it back to you.
Yeah. No, thank you. And I want to echo Tom's sentiment and comments. We got a lot of great engagement through Q&A. I've been trying to answer questions. Hopefully I have. And if anybody has follow-up, please feel free to reach out to us. So thank you so much for joining today. We hope the information was helpful and interesting to you and your organization. I want to invite you again to join our next webinar, which will be on June 17th. The topic will be AI applications in a law firm. So a little more narrow. This was our broad topic. We're going to get a series of more specific, subject matter specific presentations to come. To register, there should be a link on your console. You can register, or you can visit the website for more information and sign up. And just as a final reminder, you will get a certificate of attendance that will be emailed to you tomorrow along with a recording. So got a few questions about the presentation materials and the recording. You will be able to access both of those. And we would ask you to just please complete our short survey that you'll get via email. We use your feedback. We will review it. It helps us plan future programs that will be interesting and helpful to you. So this concludes our webinar. Thank you all so much for joining, and we hope to see you next time.
Thank you.
Bye-bye.